About equilibrium, we are primarily talking about reversible reactions. And I think I misspelled reversible, but so we're looking at reversible reactions. All right. Now, so there are some ways that we look at this, and we're going to look at a couple of equations. And this is going back to stuff that we've talked about previously, but we are solving for K, and we're going to look at K, Kc, and Kp. Kc is the concentration constant. Kp is going to be dealing with pressure constant. And so essentially what you need to know is K is equal to the products over reactant. Now, and we're going to be looking at it in various ways when we're doing that. So if you notice on Kc, we have the brackets. That's because we're dealing with concentration. Things like molarity, and those type of things. Over here, we're looking at pressure. Pressure is going to, so Kp will have things in parentheses. So when you're writing your reaction equation for Kp, remember to use parentheses. Anything else, you're going to use brackets because it's concentration. And then Kc is the equilibrium constant. I'm just underlining a couple of things. It's usually expressed in terms of molarity. Kp is the equilibrium constant, and in which so it's expressed in partial pressures measured in atmospheres or millimeters mercury. Just kind of keep those in mind. Now, I'm not going to go through here, but we have these expressions that if you kind of notice, and it's hard to read in there, we have these expressions: K is greater than 1, K is less than 1, and there should be one that's K is equal to 1. I'm going to come up here to the top where I have a little more room to write this. So what I want you to know, if K is equal to P over R, when K is greater than 1, we have what's called a forward reaction. Our forward reaction is favored, meaning it's going to drive from left to right. And what this usually means is that we have more product. If K is less than 1, what do you think it's going to be? It's the reverse, and it's going to be more reactant. So reverse reaction is favored, and that means that there is more reactant. And then the other expression you would have is K equals 1. And for this one, neither reaction is favored. And essentially what that's telling us is that the concentrations stay the same. by writing same concentration, that's kind of a misdirecting way to write it. In the reaction overall, the concentration doesn't change. Concentration of the reactants, concentration of products do not change. All right. So all of that, it's better when we're doing this to just kind of jump into it and see. But mainly what we're going to be looking at is plugging numbers into either this format or this format. So it's either going to be in for KC or KP. We're also going to address something today called a Rice table, and I'll explain what that is. What I will tell you is pretty much everywhere else in the country in Chem 1 you were taught how to do Rice tables, but the standards that we've been working on in Louisiana have not addressed this. So this hasn't been taught to any of you in here. And they're not that difficult. It's just understanding what to put when and where. All right. So let's look at these first couple. These first couple of problems, all we are dealing with is the expression for solving for concentration K or for pressure K. So we're just plugging it into the equation. Now, I will tell you this. Anytime you get these as a word problem or anything like that, the first point is always writing the expression without plugging anything in. So looking at this question, it says the following reaction is at equilibrium at a particular temperature. The reaction is hydrogen gas plus iodine gas reacts, and this is a double-headed arrow, so it's actually telling us that it's at equilibrium. It goes both ways. Anytime it's equilibrium, you're going to have a double-headed arrow. So H2 plus I2 yields HI gas, or hydrogen iodide gas. And the H2 at equilibrium, H2 concentration at equilibrium is 0.012 molar, and I2 concentration at equilibrium is 0.15 molar. And HI equilibrium is at 0.3 molar. This one's pretty easy because you're given every piece of information you need. So all we have to do is set up our equation and plug it in. So we're solving for Kc, which means that is the concentration of the products over the reactants. So it's going to be HI. The only thing that gets complicated is looking at the order. So what are we going to raise HI to? It's going to be 2 because it's got a coefficient of 2. All right, and then on the bottom we have H2 raised to the 1. We don't really have to show the 1. I'm just putting it there to it should be H2. And then we have I2 to the 1, and so on. Now, next part, again, is just plugging in our numbers. So what was our concentration for HI? 0.30 squared over concentration of H2 is 0.012 times 0.15. Now, great thing about these problems, when we're dealing with K, we do not have to show any units, so there's no units required. So what is the Kc of this one? So your answer is 50. All right. Now, giving you a little bit more information. So if we have a relationship between pressure constant and concentration constant, and we can get that by applying it to PV equals nRT. I'm not going to go through the algebra and the manipulation that they got there, but you can kind of follow through and see what's going on here. If we divide both sides by P, notice that we get moles over volume. What does moles over volume give us? Molarity, and molarity is concentration. So that's where we can get this relationship between concentration and the ideal gas law formula. So we do all this manipulation, and this is the formula you need to know. Kp is equal to Kc times RT, and this is delta N. I'll write it out here a little bit more clearly. Kp is equal to Kc and where delta N is equal to the final moles minus the initial moles. All right. So, kind of going through this, the only other thing I want to point out on this is in this particular one, we are dealing with concentrations and pressure and all of that. So we are going to use the 0.0821 liter atmosphere over mole K. But remember, we don't have to really fool with units too much in this one because K doesn't have a unit. All right. Got distracted. All right. So at 1100 Kelvin, Kp is equal to 0.025 or 0.25 for the reaction that we have sulfur dioxide gas plus oxygen gas yielding sulfur trioxide gas. Calculate K at this temperature. So when we do this, we're going to say Kp equals Kc times RT delta N. All right. Now, what we need to look at is what do we have available. So we're actually solving for Kc. I just kind of left it out the question. But we have 0.25 equals Kc times 0.0821 times, and this should all be inside of a larger 1100, and then we're looking at delta N. So our delta N is the final minus the initial. So we have 2. Well, actually, we have 2 moles here plus 1 mole here. That's our initial. And this is our final, which is 2. So we have 2 minus 3. So essentially raise that to the -1 and solve for Kc. Let's see what you get. All right. So your Kc should be 23. Now let me give you a statement. Odds are on the AP exam they're not going to ask you to solve for Kp like this. What they are going to do is give you a relationship where you're looking at the moles, and this is something that you need to know. So know that if delta N equals 0, then Kp equals Kc. So if you look at the information down at the bottom of this page, this is kind of showing you some of these things. So this is taking the reaction from number 1, yes, from problem number 1, and just kind of expanding on it. So if our original reaction, hydrogen gas plus iodine gas, reacts to form 2 moles of HI, and we get a K of 50. That's what we solved for before. What changed when I wrote the reaction like this? What have I done to it? All right, so I switched the products and the reactant. So if the reaction is written like that and you're given this information and then they rewrite the reaction like this, in order to get your Kc, all you do is take the reciprocal of it. So it's going to be 1 over 50, or so you just flip the equation. So Kc is equal to basically 1 over Kc, the new Kc. On going from this one to this one, basically we've just added coefficients of 1/2. So we basically multiplied everything by 1/2. And so when you plug it in there, you're just going to put your concentration to the 1/2 power. So essentially what you would have is, if you look down at the bottom, you see that Kc is equal to Hi, products over reactant. So it's Hi to the 1 and H2 to the 1/2, I2 to the 1/2. You can plug a 1/2 into an exponent and it works out. So essentially you're looking at the square root of the original Kc. So square root of 50 should give you 7.07. Those are just simplifications if you come up to need them. Another change that they do is when you're talking about adding equations. So if you have the equation A reacts to form B at equilibrium, our Kc1 would be B over A, and then we have C to D. Our Kc2 is D over C. And so if we add the equations together, where we get A plus C reacts to form D plus B, then when we set it up, we're going to multiply those concentrations and divide. So going from there, we're essentially going to multiply the two K's together, and that gives us Kc3, or our new Kc. All right, and all of this is just manipulations of the equations. So let's look at some more ways to calculate this. Do any of y'all remember flippy thing, Hess's law, and all of that? All right. So when you're given information like this and you're being asked for the K, we're essentially adding the equations up here. So K3 is going to be this kind of information, or K3 is equal to KC1 times KC2, but we got to make sure that everything is right. So we have this, it's times. So we have this, we have these step reactions to get there. So looking at the first one, what do we need out of the first one? Here, I'll write that more clearly.
Oh no, I just can't see it off the
KC3 is equal to KC1 times KC2. Now, so we need to look at these reactions and see what we need. So in our goal reaction right here, GOAL. So looking at this step 1, what are the things that we need from step 1 in step 2? We need the H2 and we need the H2O. What's wrong with their positions in this one? They're on the wrong side. So we have to flip that. So that means we have CO plus H2O. I'm flipping this. All right, so we have cobalt plus H2O reacts to form H2 gas plus cobalt oxide. All right, now, since we flipped that, how are we going to change K1? It's the reciprocal. So K1 is equal to 1 over 67. All right, the next one, we need the CO and the CO2, and they're in the right place, so we're going to leave it alone. So COO plus CO Now, we get to cancel this out. We get to cancel this out. And that leaves us just making sure, and since we didn't do anything to change it, that means that this one is still 490, right? So we have 8. I'm just checking to make sure I match my goal equation here. I'm looking at my goal equation here, and I'm trying to see anything that's in this that I need to make this. So I needed H2O, and I needed H2 gas. And they're in the wrong position, so I knew I needed to flip them. All right. So there's our overall reaction. So that's going to be KC3 equals 1 over 67 times 490. So KC3 is equal to 7.3. We'll keep it at 2 sig figs there. All right. So y'all see how we get those? Easy peasy. I really shouldn't say that. I've been hanging around my kids too much this week. All right. Now, last one says calculate the Kc for the reaction. If Kc for the calculate Kc for the reaction N2 plus O2 yields 2NO if Kc for the reaction 1/2 N2 plus 1/2 O2 yields NO is this. So we are basically just looking at what the shift is from here to here. So what are we doing to this one? To go from 1/2 to 1, we're not dividing, we are multiplying by 2. So all you have to do to solve this one is Kc is equal to Kc2 is equal to Kc1 squared. So now we're just going to plug it in. Kc2 is equal to 1.3 times 10 to the 4th squared. All right, so does everybody see why I did what I did? And that gives us a K of yeah. I got like 1.7 to the 8 or 1.690000000. And there's our answer. All right. So we're going to use a Rice table when the reaction is not at equilibrium yet. So you're going to be given information about initial concentrations, and that's going to key you into the fact that we are going to need to use a Rice table. So let me give you a little bit of information about a Rice table. Rice is R-I-C-E. R stands for reaction, and that's simply just the chemical reaction that you see, or chemical equation. I is initial concentrations. That's going to be written in molarity or pressure. C is the change. The change that occurs, and that's going to be based on coefficients in the reaction. And then E, essentially, if you think about this, E is going to be equilibrium. What's happening at equilibrium? All right. So let's look at one, and you'll see how this is done. Number 6, in a 1 liter container holds 1.06 moles of H2 and 1.57 moles of CO at a temperature of 162 degrees. At this temperature, the following reaction occurs. Hydrogen plus carbon monoxide goes to equilibrium, forming CH3OH. Now, so let's look at what we have here. So we're going to set up our Rice table. After equilibrium is established, analysis shows that 0.2 moles of CH3OH is in the container. What is that? Methanol is in the container. Calculate the concentration of CO at equilibrium, the concentration of H2 at equilibrium, and the Kc. Now, the thing to notice is we have initial concentrations, but we do not have concentrations at equilibrium. So we're going to start off by writing our equation, or writing our reaction. So we have 2H2 plus CO reacts to form methanol. That's our R. Our I. So what is our initial concentration of hydrogen? Okay. Now, something to notice, this is written in moles here. We have 1.06 moles, but we do know the volume, so we can solve for molarity. 1.06 over 1 liter is a concentration of 1.06 molar, plus concentration of CO is 1.57 molar. And then, are we given a concentration of methanol? Hey guys? So what are we going to write for our concentration of methanol since we're not given one? 0. We didn't have it. We were given initial concentrations. We were letting it go to equilibrium. So that one's 0. Our change. So what we are looking at is, what are the concentrations going to do? So since we're starting off with 0 here and we're going to end up with something, our change is going to be, this is going to decrease, this is going to decrease, and this is going to increase. And we need to know what factors it's going to increase and decrease by. So we look at the coefficients. So this one's going to decrease by 2x. This one is going to increase by x. Decrease by x, and this one's going to increase by x amount. And then our equilibrium, we just kind of add the things up. So we have 1.06 minus 2x. This one's going to be 1.57 minus x. And this is just x, because 0 plus x is x. All right, so the things that we are trying to find out. We want to know the concentration of CO. We want to know the concentration of H2. We want to know and we want to know the Kc of the reaction. Now, looking at the problem, after the reaction is established, analysis shows 0.2 moles of methanol in the container. So what that is telling us is that we have 0.200 mole per liter of CHO3. So that is our X. So this one's pretty easy. All we have to do is plug in that 0.200 in the X, and then we can get our concentrations. So 1.57 minus 0.200 gives us, oh, yeah. So yes, that one's going to be 1.37. And that's mole per liter. 2 times 0.2 is 0.4 minus 1.06 minus that. So we get 0.66 mole per liter. It didn't. It went from 1.57 to 1.37. No. This is the first one. I just wrote them in the wrong order. I just wrote them in the order that the problem asked them. All right. Now, so how do we solve for Kc now? Kc is equal to products over reactants, right? So that means that you're going to, so your equation is concentration of CH3OH over concentration of H2 to the second over times CO to the first. So that means that plugging it in, Kc is equal to 0.200 divided by 0.66 squared. Yeah, I'm just making sure I'm putting everything in the right place. So our Kc is equal to what? And I didn't. I actually didn't write this down. I know I solved it. Two. Yeah, so my answer is what I'm putting right here in the box, but what I'm going to look for first is the answers, and then I'll go back to see where your mistakes are. All right. All right, so you should have gotten Kc of 0.34, something like that. Unless I did my math wrong. 0.335136367, and I just rounded it up. Yes. So let's look at our initial concentrations here. What's the initial concentration of nitrogen monoxide? 0.526 atmospheres. What's the initial concentration of Br2? 0.329. And then what is our initial concentration of NOBr? Initial concentration is 0 because we're just adding those two things together. All right? Our change. Since this is 0, we're starting the reaction. The reaction is going to push forward, so it's going to be minus, minus, plus. And so this one's going to be 2x. This is going to be x. And notice that this one has a coefficient of 2, so this is 2x as well. Plus 2x. And then our equilibrium states, we have 0.526 minus 2x. Write this in a different color so that we can actually see what's going on here. 0.329 minus x. And then this last one is 2x. All right. Now, again, so looking at this one, we were given the new concentration of Br2. So the only thing we can do is manipulate it here. So we're looking at 0.329. I'm just making sure I did this right. 0.329 minus 0.329 minus x equals the new concentration, so 0.203. So that means that x is equal to what? 0.126. All right, so now we can go ahead, and this is partial pressure of NO. We can solve for that. We can solve for partial pressure of Br2. We can solve for partial pressure of what is the other one? NOBr. So pressure of NOBr equals. Now this one again is 0.203. So when we solve these, this is what you should have gotten for NO. I got 0.274. Anybody disagree? And for this one, I got 0.252. So 0.126 times 2 should give you 0.252. And 0.203, that was already given to us. We were just solving for x there. And then PNO is going to be 0.526 minus 2 times 0.126. All right. Now, the actual equation is asking us to calculate Kp. So Kp for the reaction is going to be equal to products, partial pressure of NOBr over, and that's going to be raised to the second power, over the reactants. And why am I using parentheses here rather than, because it's in pressure. I'm going to just just going to write it down here. All right, I got 4.17. All right. So what I want y'all to see with this, is that you're going to still use everything we were doing before. It's just in the rice table you have to get your concentrations at equilibrium before you can actually solve for Kp or Kc. The number 7 is done the same way, except for number 7 at the very end. You can solve for Kc, and then you'll have to use that formula that Kp is equal to Kc RT delta N. All right. And I will tell you, you probably don't have to do a calculation with this one because you'll realize something. No, we don't have to do any of the flip thing or anything with this one. All we have to do is find out our change in moles. We have 2 moles here and we have 2 moles here. So our delta N is 0, so that means that Kp is going to equal Kc. But we have to solve for everything else there. All right. I'm going to let you do this one on your own. We'll check the answer to this one tomorrow. What I do want to get to, go ahead, turn to number 8. So I want to show you what happens when these equations don't work out nice and neat like they've been doing. They've been actually very easy. All right. So we have the reaction PCl5 reacts to form PCl3 plus chlorine. And so this is our R. And looking at the problem, the equilibrium constant for the reaction PCl5 at equilibrium to PCl3 plus Cl2 is 33.3. So this is our Kc at equilibrium. If 4 moles of PCl5 are placed in a 2-liter container, calculate the equilibrium concentrations of all species. So what we're saying is we have 0.4 moles in 2 liters, so molarity equals 0.4 over 2, which gives us what, 0.2? So that means our initial concentration is 0.2 mole per liter, and that's 0 and 0. All right, so I want y'all to tell me this one. What is our change in this one? Looking at the equation, looking at the reaction, what is our change? What's going to happen to this one? Is it going to go up or down? Down. So it's going to be minus That's going to be minus x. There's no coefficient. What's going to happen to PCl3? It's going to be plus x. And Cl2 is plus x. Our equilibrium setups is going to be 0.2 minus x, and this is x, and that's x. Now, at this point, the only information that we have now is a Kc. So we know that Kc is equal to concentration of PCl3, the products over the reactants, Cl2, over PCl5, right? So now we're going to plug it in. So 33.3 equals PCl3 is going to be x times x over 0.2 minus x. Is everyone with me up until this point? Concentration of x times concentration of x divided by 0.2x. So when you cross multiply and all of that, you end up with 6.66 minus 33.3x equals x squared. And has anybody ever seen something that looks like this before? Huh? It's a quadratic. So if you put it in its expected format, it would be 0 equals x squared plus 33.3x minus 6.66. All right. So, guys, whenever you ultimately set up your quadratic formula program in your graphing calculator, just to kind of tell you how to do, it's going to basically, when you execute the program, it's going to ask you a series of questions. It's going to have something that says like A equals question mark, and for that one, your A is going to be 1. So I'm going to punch in 1 on mine. I don't have it on my large one. I'm going to have to plug this into my large one. All right, then it gives me a B equals what? My B is 33.3, right? Is that the B? Yes. And then my C is 6.66. Yeah, because it's gonna give you the answer for x. This is gonna solve for x. Now the other thing to remember about quadratics is you're gonna have x equals, and it's gonna be two different numbers. So the two numbers that I get when I do this, and it's going to be something like, and I don't know why mine is doing this, but it should have been 0.199, but I ended up with 2.01. Actually, I ended up with 0.199, and the other one that I ended up with is a negative 33.5. All right. Chris, I'm going to give you a link that allows you to punch it all in and set up the program yourself. I'm just not going to take the time and do it right now. All right. So what I'm telling you is right now, if you really wanted to solve it, you could test my math and you can plug this in. So at this point, I'm actually going to just finish this problem for you so that you can see how it works and allow you to do your other one. Allow you to do it on your own. All right. So finishing up what we need. So here's the thing you need to know. You're always going to pick the positive x. You're always going to pick the positive number. The negative number means nothing in concentration, so we're always going to pick the positive number. So that means our x is 0.199. So that's our concentration of PCl3. Our concentration, 0.199, is also the concentration of Cl2. And then 0.2 minus gives us a concentration of so this one is going to be 0.00100 is our concentration of PCl5. All right, and then there's your answer. All right. No, we already had K. K was 33.3. That was given to us in the problem. All right. So this is what I'm going to do. I'm going to go ahead and link that website to Google Classroom. If you have a graphing calculator today and you want to follow those steps to put it in there, you can grab one of the Chromebooks and do that right now. But other than that, I am finished for today. I'm going to do that and we're done.